Alright, so I'm doing another video. This is out of Griffith's EM textbook. This is problem 2.1. And before I start, if you'd like more videos like this, please like and subscribe. I'm going to go through and do Griffith's both quantum and EM, as well as Taylor mechanics. I'm going to try to just rotate for a couple weeks maybe, and then depending on what people want the most, I'll post more of. And if you'd like to message me a specific question from that or any other textbook, you can do that on my Twitter, which is right here. So give that a follow. All right, so let's go ahead and get started. 2.1. So you have 12 equal charges that are situated at the corner of a regular 12-side polygon. For instance, one on each number on a clock face. What is the net force on the test charge Q at the center? So I don't know if I can really draw a clock very well, but I'll try. Okay. So you obviously have like 12 o'clock, 1 o'clock. This is supposed to be 6 o'clock, 2 o'clock, 3 o'clock. Okay, so not spaced out perfectly, but it's fine. Let's see, 11, 10, 9, 8, 7. So each one of these points, we have a test charge, or we have a source charge, which is giving us an electromagnetic field. The test charge is at the center here. Okay. So each charge has, each source charge is Q. So they have the same charge. And if you look at, for example, 6 and 12, 11 and 1, 10 and 2, you can see what's happening is due to the symmetry of the clock that, let me see if I can maybe clear and give myself a little bit more room. You're going to have some cancelization. So for example, it doesn't mention if these are positive or negative, but we'll say negative. Maybe you have one here. 5 o'clock, you'd have another one going this way. And each one from each number on the clock is going to produce an electromagnetic field. But they all have the same charge, because remember, the force from an electric field is just 1 over 4 pi epsilon naught, the constant. The source charge, which we're calling little q, the test charge, big Q, over r squared, which is the distance from the source charge, the test charge. So the charge is all the same, and the distance there will be the same. And hopefully you can see that, and I should give this an r hat. The directions are going to essentially cancel each other out. So if you were to add up the electric field, the force through the electric field from each point, it's going to be just 0. So hopefully that is intuitive enough. Yeah, they wanted the net force, so the force here is 0. So I think that's pretty straightforward. Now part B says, now let's remove one of the charges. So we have a charge here, 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 here. But we have an empty bit here. So we remove that test charge. The way to look at this is using the property of superposition, that you can just add the force from each test charge individually and then add them all together at the end. So the way that I would think about this is you have a net force of 0, and then you're removing one test charge. So essentially the only difference is that one test charge. So in this case, it would be 1 over 4 pi epsilon naught. And then we say this, and then we'll call r squared the distance from 6 o'clock to the test charge. We'll just call that distance r. Okay, so we were at 0, And then we removed one charge, so now we have a net charge, or a net field, a net force, I should say. Because now you can think of it as unbalanced, but I think the best way to think of it is in terms of the superposition. So you had this, if you added up, for example, force from 12 o'clock plus the force from 1 o'clock plus the force from 2 o'clock, so on and so forth, that all equaled 0, right? And they all had their values. So the only difference is this term is now 0. Draw that a little nicer. I don't want to write it out because I'm lazy, but now that term is no longer there. So this is no longer no charge. It's actually going to be whatever is necessary that would have balanced out our forces. So in this case, we'll say 1 over 4 pi epsilon naught test charge times the source charge over the distance squared. Now part C is basically the same thing as part A. The only difference is now there's 13 sides, but again, the forces here will be 0. And as for D, so it's the exact same reason. The superposition from all these different positions are just going to cancel each other out. Now for D, it is also very similar to part B, where you remove one of the test charges. So just like over here, when we remove the test charge from 6 o'clock, you're essentially getting, instead of having a positive charge, it's like adding into it a negative charge. So again, you have the sum of all these forces equaling 0. But now one of the terms in here is 0. So now you have, we'll just say the sum of all the forces minus, we'll say the 13th force equals what? Well, this is maybe a better way of writing it out. We already know what this is. This is 0 from here. So then what we see is that negative that 13th charge, well, we know what that's equal to, minus 1 over 4 pi epsilon naught over r squared. I'll call it r hat. So yeah, it's the same thing here. This is what I think I was trying to do here is you have the sum of all the charges, and then you're subtracting off the force at 6 o'clock, which is equal to something, but we already know this to be 0. So then F6 equals minus, and this should be r hat, 1 over 4 pi epsilon naught, source charge times test charge over the distance between them squared, r hat. Okay? So that's basically how you do this. This is a problem of basically superposition. Hopefully that made sense, and I will do some more videos soon. So thank you.